In this video, we're going to quickly derive the formula for the energy stored in an inductor when a current is flowing through it. So here's our inductor with a terminal of A on the left and B on the right. And what we're going to do is ramp it up from an initial current of 0 to a final current of big I. So at any given moment, this inductor has a current of little I flowing through it. And since we're ramping up the current here, we're going to say di dt is greater than 0. In other words, the current is increasing. Now we've already learned that the terminal voltage across an inductor is given by L di dt, where because di dt is greater than 0, that voltage is going to be higher on the left side of this thing. Next, the power flowing into the inductor is given by the product of current and potential difference. So we can say P is equal to I times the terminal voltage VAB. And now we're ready to cook because power is telling us the rate at which energy is being delivered to this inductor. In other words, it's the time derivative of the energy. So we rewrite the power as du dt, the rate of change in the energy. And then on the right side of the equation, we replace the terminal voltage with L di dt. Now we just multiply both sides by dt, and we've related a small increment of energy to a small increment of increase in the current. So we can sum up all these increments by integrating on both sides. And on the left side, for the energy integral, I've integrated from a starting value of 0 to a final value that I called U final. And on the right side, for the current integral, I went from an initial value of 0 to a final value of big I. So we go ahead and guess antiderivatives here. And the left side is simple enough. The integral of du is just u, and I evaluate from 0 to u final. And then for the current integral, the integral of Li with respect to I is going to be 1/2 Li squared. And we're evaluating this from 0 to big I. So evaluating across the limits of integration, we end up with U final, the final energy in this thing, is equal to 1/2 L times I squared. So there's the energy in an inductor with an inductance of L when it carries a current of I. Now in the next video, we're going to use this result in the context of a simple solenoidal inductor to derive an expression for the magnetic field energy density. I'll post a link to that video at the upper left, and I'll see you there.